Hi everybody. It is time for us to look at 2.2 about proving lines parallel. So in this section, we're kind of going to do the opposite of what we did in the last section. Last time we said if we have two parallel lines, then we know these things about the pairs of angles. In this section, we're going to say, what if we don't know that our lines are parallel? What if we just have two lines? How can we use those angle pairs to prove that the lines must be parallel? So all the theorems we're going to do today are converses, the converse of the theorems we did yesterday. And each of these is going to be the converse and be very similar to what we did yesterday. So today we're going to have these two lines, and we just don't know if they're parallel or not, but we're going to have a transversal on those lines. If two lines with a transversal, I'm looking at this first concept right now, the converse of the same side interior angles postulate. If two lines with a transversal have same side interior angles that are what? That are supplementary, then those two lines must be parallel. If my two same side interior angles are supplementary, there's no choice then for those lines to be parallel. So that's one way that I can prove that lines are parallel, is by measuring their same side interior angles and finding that they're supplementary. The rest of these theorems work the same. The converse of the alternate exterior theorem says if two lines with a transversal have alternate exterior angles that are what? That are congruent, then the two lines are parallel. The converse of the corresponding angles theorem, if two lines with a transversal, transversal, have corresponding angles that are what? Corresponding angles congruent, then the lines are parallel. And the converse of the alternate interior angle theorem, if two lines with a transversal have alternate interior angles that are congruent, then the two lines are parallel. And we've missed one on here, the converse of the same side exterior angles theorem. But again, if they have same side exterior angles that are supplementary, then the lines are congruent. We also have two other theorems that are pretty simple today. It's the parallel to the same line theorem and the perpendicular to the same line theorem. So the parallel to the same line theorem starts with if two lines are parallel to the same line. If two lines are, and I'm going to use the parallel symbol, remember it's not an 11, it's parallel, are parallel to the same line, then what happens? Well, let's see. Here's line A. Here is line B. So B is parallel to A. Here's line C. C is also parallel to A. If two lines are parallel to the same line, then like B and C, they must be parallel to one another. So then they are parallel. Pretty self-explanatory on that one, right? It's kind of like substitution. If I know that B is parallel to A, and I know that C is parallel to A, I know that B is also parallel to C. And then the perpendicular to the same line theorem starts out similarly if two lines are perpendicular to the same line. So if two lines are perpendicular, that upside down T, to the same line, then what? Well, let's see. Here's a line. And here's a line that is perpendicular. Maybe this is line A, perpendicular to the first line. Here's line B, also perpendicular to the first line. What can I say about A and B? I can say that A and B are parallel. So I can say then they are parallel. Are parallel. So let's see why these theorems work. Why do I know always that if those relationships are true, that definitely means that the lines will be parallel. So here it says, suppose two lines are not parallel. So these two lines, T and M, are not parallel. Is it possible for their corresponding angles to be congruent even though they're not parallel? So we're going to look at those corresponding angles, and we see that here's an angle of 120 degrees, and the corresponding angle on the top left of the intersection up here is clearly bigger than 120 degrees, right? We have 120, but we also have more than that. So these angles are not congruent, which means there's no way for the corresponding angles to be congruent. So what we can say is no, because the top corresponding angle will be greater than 120 degrees. Because the top corresponding angle will be greater than 120 degrees. And there are lots of ways to explain that. That's just one of many, many, many ways to explain that idea. Number 3 is interesting. It says, could angle 3 be supplementary to the 120 degree angle? Why or why not? I think this is a more interesting question. So, supplementary means that the angles add to 180. So 3 and 120, they're asking, could these add to 180? But the problem is that 120 and angle 3, they're part of a triangle. And one thing we know about triangles is that triangles have an interior angle measure of 180 degrees. So let's write this out. The 120 degree angle plus angle x plus angle 3 together equals 180 degrees, because those are the 3 angles in a triangle, which means that just 2 of those angles, 120 plus angle 3 together, they cannot equal 180. They have to equal less than 180 in order to, when we add x to them, equal 180 degrees and make that triangle. All right, let's keep going. Example 2 has us writing a flow proof. Now, a flow proof is a little bit different than a regular proof. It's just another way to write a proof. We don't do very many flow proofs, but they do show up sometimes in this material, and so I wanted to talk about them. A flow proof is basically just a visual representation of what is going on whenever I create a proof. So I'm thinking, where did I get certain information? How can I organize it more like a graphic organizer, more like a web when I'm looking at this? So what I can do is I say, well, what am I trying to prove? I'm trying to prove that if I have angle 1 being congruent to angle 2, then that shows me that L is parallel to M. And I'm proving the converse of the alternate interior angles theorem. So I cannot use that theorem in my proof. So what we can do is we can start with some boxes, right? We can kind of write this wherever on the page we want, like we're making a web diagram in English or something. So I'm going to go ahead and say, we'll start here. Angle 1 is congruent to angle 2. And underneath that, I'm going to write y. That would be the given information. What else do I know? What else can I use in this proof? Well, I can look at the diagram, and I can see that angle 1 and angle 3 are congruent, right? That's given to me in the diagram by showing me that they're vertical angles. So I'm going to go down underneath here maybe, and I can write angle 1 is congruent to angle 3 because those are vertical angles. So then I'm going to go ahead, and this is the part where it becomes a flow proof. I'm going to put some arrows here because if I take both of those pieces of information, knowing that angle 1 is congruent to angle 2 and angle 1 is congruent to angle 3, then I can use substitution to show that angle 2 is congruent to angle 3. So I'm going to put that there. Angle 2 is congruent to angle 3 by substitution. And because those are congruent by substitution, I can say, wait a minute, angle 2 and angle 3 happen to be corresponding angles on those parallel lines. And I know that corresponding angles on lines mean that the lines are parallel. I know that if the corresponding angles are congruent, the lines are parallel. So finally, I can say, hey, 2 and 3 are congruent. That means L is parallel to M because I know that they're corresponding angles and they're congruent, which means the lines are parallel. That is the converse of the corresponding angles theorem. And that's the end of our flow proof. Our flow proof could have gone vertically, it could have run diagonally, it could have really done anything. It's just another way to show our information and show how we're getting from one piece of information to the next one. Again, we don't use them very often, just sometimes. Example 3, we want to figure out whether the lines are parallel. Says the edges of a new sidewalk must be parallel in order to meet accessibility requirements. Concrete is poured between straight strings. We've got straight lines. How does an inspector know that the edges of the sidewalk are parallel? Well, let's see. If the edges of the sidewalk are parallel here to the road, then what we could do, or what the inspector could do, is he could measure angle 1 and angle 2. And he could say, hey, if angle 1 is supplementary to angle 2, then that means these are same side interior angles and the lines of the road are parallel to the lines of the sidewalk. So maybe we'll write that. We'll say if angle 1 and angle 2 are supplementary, if angle 1 and angle 2 are supplementary, then the lines are parallel. And remember, we said why. We said it was the same side interior angles theorem. Remember, it's actually the converse of the same side interior angles theorem that allows us to say that the lines are parallel. So by the converse of the same side interior angles theorem. Next, state the theorem for which the converse can be used to show that the measure of, that M is parallel to N if the measure of angle 4 is equal to the measure of angle 8. We'll look at the positions of 4 and 8. They happen to be corresponding angles, so we would need to use the converse of the corresponding angles theorem. Converse of the corresponding angles theorem. Right, then we've got example 4 where we're going to solve problems with these parallel line theorems about this barn gate. So if we're looking at this gate, or if Bailey's building this gate, it says when building a gate, how does Bailey know that the vertical boards V and W are parallel? We can see that V and W, they're both perpendicular, right? They're both perpendicular to A. And we had a theorem about that. We said if two lines are perpendicular to the same line, then those two lines must be parallel. So we can say they are perpendicular to the same line. They are perpendicular to the same line. So they are parallel. B says, what should the measure of angle 1 be to ensure board B is parallel to board A? Well, if board B needs to be parallel to board A, the same side interior angles need to be supplementary. So it would be 180 minus 35, and it would be 135 degrees by the converse of the same side interior angles theorem. Letter C, Bailey also needs board C to be parallel to board A. What should angle 2 measure? Well, if A is down here and C is here, and I know that A is perpendicular to V, then C also needs to be perpendicular to V for C to be parallel to A. So it would need to measure 90 degrees. I'm going to say 90 degrees because A and C will both be perpendicular to V. And C will both be perpendicular to V. And finally, it asks us if B is parallel to C. Well, we know from letter B that B is parallel to A, and we know that letter C tells us that C is parallel to A. So if we use both of those pieces of information, we can say, hey, B is parallel to A, C is parallel to A, they're both parallel to the same line, so they must be parallel to each other. So yes, B and C are both parallel to the same line, so they are parallel to each other. Perfect. And that is everything for this section. So go ahead and work on the problems you have to go along with this. And if you've got any questions, let me know. Have a wonderful day. See you later.